What the heck is up, guys? It's Jacob here, and in this video I'm going to be talking about the electric potential or voltage. So I've used this slide before. It's a really good slide of kind of giving you guys the idea of what electric potential is, but I'm going to explain it in a different way this time, a little bit different. So on the left here, we could imagine this here as object as a ball. So imagine if you had like a bowling ball, right? And if you lifted that bowling ball 10 feet into the air, it would have what we know as potential energy. So let me just clear this. So it would have potential energy. And all that means is it's stored energy, and it's energy stored in that ball. And you can harness that energy in pretty much any way, but the most obvious way is if you release that ball, it's going to turn into kinetic energy, and that ball is going to start moving due to the downward force of gravity. You can also see this used in things like clocks. You might have large weights. Sometimes they have weights, and they lift them up and they hang them, and they use those weights to drive a mechanical clock. So that potential energy is stored in the mass of that object, really, by lifting it up. So we can see that the potential energy in this case is equal to the mass of that object times the gravitational constant. That's not really the gravitational constant, but the acceleration of gravity, I should say. It is a constant, and times the height of that which you lift that object to. Now, what's really important here, what I want you guys to see, is that it's directly proportional to the mass of the object as well as the height which you lift that ball to. So we see height. When you lift it up higher, it's at a higher potential, and that bowling ball, because it has a lot of mass to it and is being pulled down by gravity, it wants to go down to a lower potential. So it wants to fall down to a lower potential, and it will have potential energy stored in it when you lift it up. And so the larger the mass of that ball, you can see, because it's directly proportional to m times g times h. G is just a constant, so we can kind of just factor that out and forget about that for now. But so if we have two bowling balls, and one is, let's just say, a 10 kilogram ball, and the other one's a 20 kilogram ball. That's a really heavy bowling ball, but just bear with me here. So if one is a 10 kilogram bowling ball, and the other is a 20 kilogram ball, you lift them both up to 10 feet. Obviously, the one that has more mass is going to have more potential energy. It's going to have the ability to do more work. It's going to have the ability to do twice as much work, actually. And likewise, if you had two bowling balls of an identical mass and you lifted them up to different heights, so let's say you lifted one up to 10 feet and one up to 20 feet, the one that is at 20 feet is also going to have twice as much potential energy. Even though both of those bowling balls have the same mass, let's just say they're both 10 kilogram bowling balls, if you lift them to different heights, they are going to have a different amount of potential energy, or one is going to be able to do more work. And so we can really analogize this to electric potential. They're both two very physically similar processes going on here. Just a smaller, this is the electric one on this side here is a lot smaller scale, and it has different forces acting on it. So instead of gravitational forces, it has electric forces, but it really is the exact same thing. It's exactly the same, and that's why I want to use this slide. I don't really like that water analogy where they talk about water pressure in a pipe, because it obscures what's really happening. These are two very identical processes. And so if we look over here at the electrical side, this electron here also has some potential energy associated with it. Just like the ball, it has the ability to do some work, and it's not much work at all if you compare it to how much energy is stored in a bowling ball lifted up 10 feet. It's not nearly the same amount, but as you'll see later on in my current video, even though these electrons don't really have much energy associated with them, there are like trillions of electrons moving at any given time. So it's like the number is just mind-blowing of how many electrons are moving. So really, they don't have individually, they don't have much energy, but if you have trillions of them moving through a wire at a given time, those energies start to add up. So the potential energy associated with a single electron, or any charge carrier really, is going to be equivalent to the charge of that charge carrier times a voltage, a potential difference. And so what I want you guys to really see here is that it's proportional to these two quantities. We don't really care that it's equal to them. That doesn't really matter right now. I don't really need you guys to understand that. What you need to understand is that the potential energy of this particle, the amount of work that this particle is going to be able to do, is proportional to the charge of this particle. So the greater the charge it has, the more work it's going to be able to do. And it's also proportional to the voltage at which this particle is located. So the greater the voltage, the more energy this particle is going to have associated with it, and the more work it's going to be able to do. All right, so now if we look at the bigger picture, the only difference here is that this is a negative charge, and this negative charges want to move from a higher potential to a lower potential. Again, it's kind of counterintuitive, but that's how negative charges work. In the next slide, we'll actually look at it with positive charges, because it mimics this bowling ball a little bit more, because we're used to things falling from a higher potential to a lower potential. It's really the same exact thing, but it's just going backwards. Electrons want to go from a lower potential to a higher potential. But you can see here, what I want you guys to understand is that we can analogize the actual voltage, to the height of this ball. And we can analogize the mass of this ball, the m, to the charge of this particle. So essentially, the larger of a ball you have, the more potential energy you'll have. Also, the higher you lift that ball, the more potential energy you have. Same deal going on over here with the electrical side. The larger the charge this particle or this charge carrier has, the more charge it has, the more energy it will have. And likewise, the higher the voltage that this charge is placed at, the more energy that this particle will have, and the more work this one charge carrier will be able to do. It will be able to do more work if it is at a higher voltage. So it's pretty much directly equivalent to the height in this bowling ball scenario. All right, with that said, let's move on to the next page. So let's look at the actual definition of a volt. This is the formal definition, so the definition of the volt. So let's look down here. I'll just read it to you guys. I kind of put it in my own words, but this is pretty much the exact definition. Voltage is the potential energy of a charge carrier divided by the amount of charge that the carrier possesses, the charge carrier possesses. So what that basically means is, if we go back to this slide here, what this means, let's put it in terms of this bowling ball. If we looked at how much potential energy this bowling ball had, how much energy this actual bowling ball could do, so the potential energy stored in this bowling ball, and we divided out the mass of the bowling ball, so we just kind of divided that out, what we would be left with pretty much is the height. Of course, we'd have gravity still there, but let's not worry about that right now. Like I said, that's a constant. So what we'd be left with is the height. We can kind of think as gravity and height as acting together in this case if we wanted to. So what we'd be left with is this, and that in this case is what we are calling is voltage. And that's why I said you can really analogize voltage to the height at which you bring this ball to. They're the same. So the potential energy is the amount of energy in each of these particles divided by their charges, and that is what voltage is. So it's pretty much how much work each of these charge carriers is able to do divided by their charge. It doesn't really make much sense, and that's why I also put this other definition below. And one other thing I want to explain real quick to you guys is these three charge carriers, they are the same charge, but they are positive. I want you guys to realize that these are moving from a higher potential, you can see here, to a lower potential. They are not like the electron. I used positive charge carriers in this case because it's really hard to conceptually understand what's going on in this case with negative charge carriers, because you have like negative potential energies, and you have it's really weird, negative voltages, and it's going the opposite direction. It's not really intuitive, and it's hard to follow. So I used positive charge carriers in this case, just so it'd be a little bit easier to understand. So if we look at this other definition, voltage can be thought of a region where a charge will have a specific amount of potential energy available to do work. And this is a really good definition. I really like this. It's not the formal definition, but I really like it because it explains it really well. And so what we can think of is so these are three charges, and they're all the same charge, but they have different amounts of potential energy. So in this first case, it has the maximum potential energy. This charge is located up here where the voltage is 100 volts. So it will have the most potential energy associated with it. As that charge moves down, it moves down to a region. It's basically just another area. Down here, the voltage is 50 volts in this region, and this particle will have the ability to do half as much work now, because its potential energy is half the original potential energy. And likewise, if you have that particle and it's down at a potential or a voltage of 0 volts, that particle has zero potential energy, or the ability to do no work. So it cannot do any work really. And so one other thing I want you guys to realize real quick here is that there's always an electric field present whenever there's a potential difference, whenever you have a voltage. You cannot have a voltage without an electric potential, you cannot have, or an electric field, and you cannot have an electric field without a voltage. They will always go hand in hand. And really what voltage is this is the big picture. This is what I want you guys to understand. Voltage is really, all it is an area. It's just an area where the electric fields will give these particles, these charges, a specific amount of potential energy. That's all it is. Voltage is really just kind of like a region or some place where the electric field has a certain strength. It's basically kind of like gauging the strength of the electric field. And it's saying, if you place this particle in this potential difference, or at this voltage, this particle will have that much potential energy. It's placing a value on how much potential energy a specific charge carrier or particle will have. So it's kind of like taking this bowling ball example and saying you have a mountain, let's say you have a mountain here and a higher mountain up here and a higher mountain up here, and this mountain is the 3-volt mountain, this is the 5-volt mountain, and this is the 10-volt mountain up here. So if you take it to the 3-volt mountain, you will have, if it rolls down that mountain, it will have 3 joules of potential energy available. And if you take it up to the 5-volt mountain, it'll have 5 joules of potential energy. It's not quite that simple, but that's basically what it's saying. So the higher the potential difference, or the higher the voltage you take it to, the more energy that exact charge carrier or that bowling ball or whatever it is, it will have. So really, voltage, all it is it's giving these charge carriers their energy, the ability to do work. So now let's look at how voltages influence charged particles. And out of this, I just want you guys to get something real quick here. So we have 2 identical particles. These are both electrons. So one is in a potential difference of 100 volts, the other one is in a potential difference of 200 volts. And so they have the same charge. They're both electrons. As you can see, they want to move from a higher to lower potential. There's the direction of the electric field right there. But the particle in the lower potential has half the force on it as the particle with the higher potential. So this particle here, when it's at this potential difference, it'll have more energy associated with it. The voltage will be strong. The electric field will be stronger. I didn't really show that here. This electric field should be stronger, but it'll have a stronger electric field and it'll have more force on it. So this particle, overall, this particle will have twice as much energy. It'll have twice as much energy. It'll have, this particle on the right can do twice as much work as the particle on the left, because it is at a higher potential voltage. It has twice as much potential. So if you place that same identical particle in 2 different voltages, it will have a different energy associated with it, and that particle will be able to do a different amount of work. So really, voltage is what gives these particles the ability to do work. So now let's look at what causes electric potentials, because if you guys have watched my other videos, you know that I say electric potentials or voltages is what really makes electricity possible. Electricity would not be possible without electric potentials. You have to have a voltage or electric potential present for a current to flow. It's impossible for current to flow without electric potential. You can't have an electric potential without a current. Again, electric potentials, all it is just an area where the electric fields will influence these charged particles a certain amount. So let's look at some of the things that cause electric potentials or voltage. As I said before, electric fields, anytime an electric field is present, you will have a voltage present. A voltage is just merely a region where the electric fields will give these particles a certain amount of energy. So we can look at this charged particle. If you guys have watched my first video, you'll know that I kind of discussed these charges and how they have electric fields that come off of them. So this is a positive charge here, and it has an electric field that extends radially outwards from that charge. So it would have a voltage anywhere around this charge. There would be a voltage present. So basically, right here there would be a voltage present. Right here there would be another voltage. Here there would be another voltage. Here there would be another voltage. So voltage, I just want you guys to understand, is a region. All it is a region where these particles will influence other particles. And then we have charge separation. Now charge separation, this is kind of the same idea. They are exactly the same thing. They are one and the same. I want you guys to understand that. Charge separation is really just still electric fields, but it's really common, so I thought I'd show you guys here. Charge separation, this is what you guys see in capacitors. You have 2 plates. two plates, with one with an excess of electrons, one with a deficiency of electrons, so there's charge separation. You'll also see this in batteries. You'll have, you know, some type of ions on one side, and on the other side you'll have like the, you know, cathode, and it has a bunch of, you know, excess electrons. And so that's basically how a battery works. So really this whole thing here, if we get rid of this, these top parts are just a bunch of these. So it's just a bunch of electric fields adding together, and the bottom part is just a bunch of negative charges where their electric fields add together. So it is still just a bunch of electric fields adding together. It is the same idea, but I thought I'd show this to you guys because charge separation is used a lot, particularly in batteries. You know, that's what causes the electricity or the current to flow, is because there's a separation of charges, and that separation of charges has an electric field between that separation. As you can see here, this electric field is pointing away from these top positive charges, because in positive charges they point away, and into these bottom negative charges, because if you guys watch my first video, you'll know that negatively charged electric particles will have electric fields that point inwards. So that's one cause of electric potentials, and then one other cause is changing magnetic fields. So magnetic fields where their magnitude changes over a certain amount of time, so they're not constant. So basically any magnetic field that is not constant will create an electric field, and as we just discussed, electric fields are always associated with an electric potential or a voltage. So anytime you have a changing magnetic field, it will create an electric field. I'm not going to discuss that anymore in this video, because I'm going to make a whole nother video, a whole nother series on magnetic fields. Those are a little bit more complicated, and that's kind of different. It's a different topic, so we'll talk about magnetic fields later, but I thought I'd show that to you guys just because it's important that you understand that. So anytime you have changing magnetic fields, and it's very important that they're changing, a constant magnetic field will not, it has nothing to do with electricity really. It won't generate any electric fields, it won't influence any particles or anything like that. It has to be changing. So a magnetic field which changes with respect to time will create an electric field, and likewise an electric field which changes with respect to time will create a magnetic field. Alright guys, and so now let's look at how electric potential or voltage can produce a current. So I've kind of explained this before, I'll explain it one more time in this video. When you have an electric potential or a voltage, you always have this electric field here. These gray arrows represent the direction of the electric field, and this electric field always points from higher potential down to a lower potential. And so this electric field, which we see here, influences those charged particles. It applies a force to them, an electric force, and it causes them to flow in the opposite direction in this case, because they're electrons, they're negative charge carriers, so they want to flow against, they want to flow from lower potential to high potential, so they want to flow against the electric field. And that is what actually causes the current. So really, as we can see down here, here's that same wire. If we zoomed in a lot, there's the higher potential, the lower potential. The electric field points from that higher potential down to the lower potential. And so if you can see down here, it actually causes these electrons to jump from shell to shell of these atoms, and overall they're moving in a rightward direction from a lower potential to a higher potential. And that is what actually causes a current. Really, it's this electric field that is causing the electric force on these charges, these charge carriers, in this case these electrons in this wire, and it causes them to move in a overall single direction, in this case to the right, because they are positive, or they're negative charge carriers, so they want to go from a lower potential to a higher potential. And overall these electrons, as we'll see in the next video, produce a current. A current is just a flow of charge carriers. So that's pretty much it. I just wanted to show you guys real quick how the electric potential actually produces a current. So if we look in this next slide here, I just want to show you guys this real quick as well. So here we have two identical wires, and it's important to understand these wires are equal resistance, and you might not know what resistance is yet, but I will make a video on resistance. So these two wires here are of equal resistance, and basically what I want to demonstrate here is that on the top we have a lesser potential difference, so it has a smaller potential difference, it has a smaller voltage across this wire. The electric fields are smaller because the potential difference is smaller, so the electric fields are smaller. And on the bottom, you have a larger electric field because it has a greater potential difference across that wire. And also, we can see that it's moving overall, if we look at this wire, twice as many charge carriers, or twice as many electrons. So the greater the voltage, really, we can see that there's a big difference here. It will move twice as many. This top one is moving half the amount of electrons, whereas the bottom one is moving twice as many electrons. So the greater the voltage, the more current you can push, the more potential energy these charge carriers will possess, and overall, the more current you will be able to move through circuits or conductors of equal resistance. So what I want you guys to take away from this video is the electric potential, or voltage, gives charge carriers, in most cases that is an electron, in some cases it's ions in a battery or whatever, it doesn't really matter. It gives these particles the ability to do work and the ability to start to gain kinetic energy and flow through a wire, and that is what actually causes a current in a wire. So electric potentials influence charged particles and cause them to essentially create a current, and what causes that is really the electric field. Alright guys, so I'm adding this part of the video in a few days later, so sorry if something doesn't blend in right, but I was watching my first video, the basic physics behind electricity, and I said that I was going to mention this, and I totally forgot to mention it, and it's a very important concept. Voltage is a relative quantity. So what that means is it has to be measured between 2 points. It can never be, voltage is not just a single point quantity. It's not like you can just go to a single point and just measure voltage from that point. It has to be between 2 points. When I say voltage is a relative quantity, it makes the same sense in this ball scenario as well. I can't just, it wouldn't make any sense if I just said the ball is at 10 feet. 10 feet relative to what? You could say the ball is at 10 feet relative to the ground, or it's at 10 feet relative to the roof of a building, or it's at 10 feet relative to, there's so many different things. It could be 10 feet relative to a hole that's 100 feet in the ground. So it's a relative quantity. You can't just say 10 feet. In this case, it made a lot of sense throughout this entire video, me just giving you these numbers, because obviously the ball is 10 feet relative to the ground at the lower potential. This here, down here, would be the ground, but it has to be measured between 2 points. As you can see, this 10 feet goes between here and here. This 100 volts over here goes between this plate and this plate, so it's 100 volts between those two plates. If I didn't have this bottom plate down here, I couldn't just say this plate is at 100 volts. That's completely wrong, because you have to measure it between 2 points. It always has to be measured between 2 points. So the voltage is relative between this point up here and this point down here. You could never just have one point and say that point is at 100 volts. Voltage always will be measured between 2 points, and it's like that in real life too. If you ever have a multimeter, you can't just take one probe and measure a point and tell me what the voltage is. You have to take that other probe and you can put it between another voltage bus, or you can put it to ground, you can put it anywhere, but it has to be between 2 points, and you will never get a voltage at one point. So let's go back to this slide over here, where I was telling you guys you can get voltages at these points. And this is a little bit more of a harder concept to understand. I shouldn't have really just said that, but what I mean by this, if you have a voltage at this point, this is relative to infinity. So basically, what these particles are really small particles, and they have a voltage, they have an electric field around them, which decreases based on the square of the distance. So it's inversely proportional to the distance squared. And if you go way out here, let's just say this is a fair distance from that particle, the electric field will effectively be zero, and your voltage will effectively be zero. So when you measure a voltage at this point, it's measured with respect to a distance great enough to where that voltage is effectively zero. So between this point and this point will be some voltage, between this point and this point will be some voltage. So it's always measured out to that infinity, or that distance that's far away, enough far away to where your voltage is zero and your electric field is effectively zero from that particle. So that's how you measure voltages just at points away from a particle. It is still measured between 2 points. I just want to make that clear. So I hope this gave you guys a little bit of a more, like a better conceptual understanding of what voltage actually is. If you didn't understand it, go through and watch it again. Again, this video right here, this is the hardest idea to get across. Electric potential is one of the more difficult ones to get across. But the current and resistance videos will be rather simple and straightforward. But this idea is a little bit harder to understand. Again, just go back through it and watch it again if you didn't understand it. And, I hope this helped you guys out. If not, definitely leave a comment below of anything that you guys might not really understand. I'll try and possibly redo this video and make it a little bit clearer if I feel like I left something major out. So I hope you guys enjoyed this one, and like always, have a good one.